For half a century, the moon was a museum of human curiosity. In 2026, it is becoming a high-stakes industrial theater. While the space economy already exceeds $600 billion, current projections suggest that the addition of lunar resource extraction could push that valuation toward $10 trillion by 2050. The primary catalyst for this commercial expansion is an isotope known as helium-3. On Earth, this material is virtually non-existent. But the moon lacks a magnetic field and a dense atmosphere. For billions of years, unfiltered solar winds have bombarded the lunar surface, directly embedding helium-3 atoms, distinguished by their 2 protons and 1 neutron, deep into the top layer of dust, or regolith. This continuous cosmic bombardment has created an immense reserve. Current estimates suggest there are 1.1 million metric tons of helium-3 trapped in the lunar crust. Extracting it requires moving past passive observation. Space agencies and private aerospace firms are designing heavy machinery to systematically crush this rock, isolating the energetic isotopes hidden inside. The objective is strictly commercial. The entity that establishes the infrastructure to harvest this specific isotope will control the foundational supply chains for the most critical technologies of the coming century. The immediate terrestrial demand for helium-3 stems from quantum computing. This is an emerging sector that financial models project will reach a valuation of $1 trillion by 2040. Scaling this technology faces a severe physics bottleneck. Superconducting quantum processors rely on extremely fragile states called qubits. To function without degrading into thermal noise, a process known as decoherence, these systems must be maintained at temperatures hovering just fractions of a degree above absolute zero. Helium-3 is the essential cryogenic coolant required to reach and hold those exact thermal thresholds. Without a stable supply of this isotope, scaling quantum infrastructure is physically impossible. A secondary, potentially much larger application lies in base load power generation, specifically theoretical aneutronic nuclear fusion. Unlike traditional fission reactors that split heavy atoms, fusing helium-3 with deuterium forces light atomic nuclei together. This specific reaction yields massive amounts of electricity while generating virtually zero harmful radioactive waste. This diagram illustrates the extreme energy density of that reaction. On one side of the scale, just 2 liquid liters of helium-3 produces the exact same energy output as the 1,000 tons of raw coal balancing it on the other side. Securing millions of tons of this material provides the necessary fuel to power a quantum-driven global economy and establish a clean energy grid. Harvesting millions of tons of material from the moon faces an immediate logistical barrier: the sheer gravitational pull of Earth. This chart maps the exponential fuel costs required to lift heavy payloads into orbit. The math is unforgiving. Launching industrial excavators, deep space habitats, and the return fuel necessary to bring the helium-3 back erases the profit margins of the entire endeavor. To bypass this financial barrier, aerospace engineers rely on a closed-loop system called In-Situ Resource Utilization, or ISRU. By definition, an ISRU operation requires a lunar base to construct, operate, and fuel itself using strictly local materials sourced directly from the moon's surface. Executing this with human labor introduces massive inefficiencies. Maintaining human life in a vacuum requires heavy life support modules, and biological limits restrict operational hours due to severe radiation exposure and communication latency. The engineered solution replaces biological crews with decentralized autonomous robotic swarms. These AI-driven units can drill, excavate, and process materials continuously without requiring oxygen, water, or sleep. The modern space race relies on mastering autonomous robotics capable of surviving, operating, and safely self-replicating in a deep space vacuum. These swarms begin aggressive mechanical extraction. As they grind into the regolith, they isolate helium-3 alongside rare earth elements, titanium, and platinum group metals. Simultaneously, specialized extraction units must target the permanently shadowed craters at the lunar poles. Inside these deep basins lie billions of tons of ancient water ice. Using electrolysis, the base separates this ice into its base components. The oxygen is routed for base maintenance, while the liquid hydrogen is condensed into highly combustible rocket propellant. Managing this output requires a complex logistical network. Automated transport craft hover across the gray landscape, relocating heavy payloads of these processed minerals between extraction sites and central refineries. In the final phase of the ISRU sequence, the leftover processed regolith dust is fed directly into massive autonomous 3D printers. These machines extrude the physical architecture of the colony, building reinforced blast pads and habitat walls from the dirt itself. The nations that successfully deploy these AI-driven systems first will establish the foundational infrastructure for space manufacturing. By controlling the initial refineries and fuel depots, they gain the leverage to set the logistical standards for all future operators. Deploying trillion-dollar automated infrastructure requires one absolute prerequisite: legally secure, undisputed territory to operate on. International space law currently operates in a severe vacuum. In 1979, the United Nations proposed the Moon Treaty, explicitly declaring lunar resources the common heritage of mankind, effectively outlawing sovereign land grabs. However, no major spacefaring power ever ratified that treaty. This intentional abstention left the moon legally unprotected against aggressive commercialization. To establish rules that favor commercial extraction, the United States drafted a modern alternative, the Artemis Accords, heavily driven by NASA and an alliance of partner nations. The Accords rely on a highly specific legal distinction. They assert that extracting a resource from the lunar surface does not constitute national appropriation of the underlying land. To protect operations, the Accords establish safety zones, designated radii around active mining equipment designed to prevent harmful interference from competing operators. While officially framed as pragmatic operational protections, these zones restrict access to physical territory. To rival nations, a safety zone operates exactly like a sovereign border. This framework is fiercely contested. China and Russia have explicitly rejected the Artemis Accords, forming a competing alliance to build their own infrastructure, the International Lunar Research Station. The conflict centers on geography. The moon's resources are not distributed evenly, and survival requires proximity to water ice. This map highlights the lunar South Pole, specifically Shackleton Crater, making its shadowed ridges the most aggressively contested real estate in the solar system. As we overlay projected operational zones, the geopolitical risk becomes stark. Blue Artemis safety zones immediately intersect with the red operational areas claimed by the ILRS. The intelligence community views this overlap as a severe flashpoint. The race to secure these narrow, water-rich zones introduces the high probability of claim jumping, where competing mining swarms could trigger kinetic conflict over prime territory. Behind the diplomatic maneuvering lies raw economic ambition. Securing this land guarantees dominance over an entirely new industrial base. With autonomous robotic prospectors already launching, the brief window to establish standardized governance is rapidly closing. The architectural blueprints for these lunar complexes are complete, and deployment has begun. The multi-trillion-dollar effort to extract lunar resources is an active operation. The powers that successfully secure this off-world supply chain will inherently control the energy and computing dominance of the 21st century.